Hi, my name is Sarah Zabo, and this is my project on spring oscillations. In this lab, we observed the motion of a mass oscillating vertically on a spring using tracker, and then created a computational model based on Newton's second law in conjunction to a new topic, the energy principle, to predict the motion of the mass oscillating vertically. We used GlowScript to predict the motion by creating two graphs, first a position versus time graph, and secondly a changes in total energy graph. This lab is important as the rudimentary findings help us predict the motion of springs in other contexts like sports. We can apply the physics of an oscillating mass to extreme rope jumping sports in which the person is a mass oscillating. Before we can get into the lab, it is important to discuss the scientific reasoning for observing the motion of a mass oscillating on a spring. Spring mass systems are excellent models of how forces from the surroundings can affect a system. The forces of focus in this lab are gravity force and the spring force, each of which with their respective equations, magnitudes, and directions. Summing these net forces helped us solve Newton's second law derivations and thus effectively solve for the velocity and position at a given time using the velocity update and position update equations. Finally, it is important to discuss the role of energies in this lab. The spring mass system not only demonstrates interactions of force as well, but also greatly depicts the changes of energy. We focus on the idea of how energy in a system will be conserved, but it will convert between energy types over time. Our total energy of the system focuses on kinetic, gravitational, and spring, and you can see their respective magnitudes below. In this lab, we tracked the motion of a spring mass oscillation for a time of 9.307 seconds. We analyzed the motion by setting an XY axis with the origin being at the fixed attachment point of the spring, causing the movement to be in the negative Y direction. Additionally, since we knew that the relaxed length of the spring was 0.7 meters, we were able to set a calibration stick to monitor the exact metric changes in the position. Also, the mass weighed 0.402 kilograms. Now here's the video at play. You can see that the tracker is recording all the new XY positions over time, which we will convert into a CSV file. To depict the mass's motion, we created a computational model on GlowScript solving Newton's second law derivations of the position update formula and the velocity update formula at very small time increments over a long period of time. The first part of the model focused on updating net forces of gravity and spring forces during the compression and stretching to determine the updated velocities and positions. The second part of the model focused on tracking the energy during the compressions and stretches, comparing changes in potential kinetic and spring energies. Coding initializations consisted of inputting the object's mass, initial position, initial velocity of 0 meters per second since it started oscillating from rest, a period of oscillations of 1.52 seconds, which we calculated by finding the difference in time it took for the mass to return to a position, the spring constant using the solved time period, giving a constant of 6.83 newtons per meter, and finally the equations for kinetic, gravitational, spring, and total energy of the system. Coding calculations is where we repeatedly updated the net forces, position, velocity, and energies of the system. A while loop produced a myriad of calculations using a small delta t increase of 0.0048 seconds. First, we calculated the net forces at a given time to solve the velocity update equation. The new velocity solved the position update equation, and the new position solved for the change in compression and stretch of the spring, solving the spring energy. Additionally, the y position solved the new gravitational energy, and finally, the new velocity solved for the change in kinetic energy. The coding visualizations was the last part of the code, which consisted of designing the Y position over time graph and the energy graphs. And here you can see it at play. The Y position over time compared the motion between the computational model in blue and observed model in red, and the energy graph over time depicted potential energy in red, spring energy in green, kinetic energy in blue, and total energy in yellow. The results depicted both motions having the same period of 1.52 seconds, but the model motion has a greater amplitude and is positioned higher on the y-axis than the observed motion. Additionally, the observed motion in red created jagged peaks and valleys on the graph, so not fluid movements. This could be due to the sum of the net forces taking into effect of drag and other dissipative forces from the surroundings, or the neglected spring mass causing incorrect calculations, and finally, human error during the tracking usage. To prove on this in the future, I would add a drag force to the FNet computational model calculations to get a more realistic predicted motion. The results of the energy graph demonstrate the conservation of energy in the bound system. Potential in red and spring in green were the dominant energies, and they look like inverse sine graphs of each other. The kinetic energy demonstrated similar wavelengths at the beginning and the end, but in the middle time period developed shorter amplitudes and longer periods. Additionally, the bound system principle was followed because the total energy summed to 0. Finally, I would improve on this graph by incorporating changes in thermal energy. Now, time for discussion. Is the energy principle satisfied? As we just discussed in the last slide, yes it is. First, the energy principle states that energy is neither created nor destroyed, thus the energy of a system is constant. Our model followed the energy principle, specifically the bound energy principle, in which the total energy remained constant and 0, but the energy types were constantly converting from one to the other. This was seen specifically with the changes from potential to spring energy. As one decreased, the other increased. The second discussion point focuses on comparing the oscillation periods of the x and y positions. We originally solved the x period to be 1.52 seconds, and using the same method, we found it took 1.389 seconds for the mass to return to the same y position. Because the y position was a shorter period than the x position, it will complete one oscillation faster. However, the periods are very similar, so at first the graphs of the motion in the x and y directions would look the same, but would diverge over time. Thank you for listening. Bye.